just waiting. Some people are still coming in. We'll stop at 5. All right. Hi, everybody. Let's start this session. The first paper is going to be presented by Daniele Cozzo. The title, Batch Pack and Proof, More Efficient Verifiable Computation for CKKS. Please.
Thanks. So I'm going to talk about some work on making verifiable computation for FHE more practical. Let's start with the context. So I'm pretty sure almost everybody has heard of fully homomorphic encryption, FHE. It's a great technology that allows outsourcing computations in a privacy-preserving manner, because allows the client who doesn't have the resources to run a computation or doesn't have the code to outsource it to a cloud, a specialized cloud. So it encrypts the input data, sends them to the cloud that's the computation, and sends the encrypted result to the client that decrypts and learns the output of the computation. So it's really, really great. It's a great technology. I don't have to explain why this is so great. But it works in a setting where one assumes that the cloud that does the computation is honest. If that is not the case, then the cloud could do whatever they want. They could, for example, they could run a different computation. They can bias the result. Or in the case of FHE, they could even try some strategy that allow them to perform key recovery attacks. So a lack of integrity is actually quite concerning because it also potentially leads to a lack of privacy. So how do we solve this issue, which is inherent to fully homomorphic encryption? Using snarks. So combining a snark with FHE yields what is called VFHE, verifiable FHE. And so as you can imagine, what we change here is just that we now ask the cloud to provide a proof that they indeed run the right computation. And then a proof is appended to the output, to the result, and the client checks first the proof, and only if the proof verifies, it will accept it will decrypt and learn the output. So VFHE is, I would call it the gold standard for secure outsourcing, because it can achieve privacy, integrity, and thanks to the succinctness property of the snark, we can also efficiently verify a proof. So we are potentially able to outsource any computation and verify it on our local machines. It's a very powerful tool. So you would ask, can we have it? It's great, but can we have it in practice? So answer is having a verifiable FHE scheme in practice is really hard. And this is due to a number of reasons. So first, you have two primitives, snarks and FHE. And they work in completely different worlds with different parameters. Snarks, as you know, well, typically they work with large prime fields. They perform well when they process arithmetic circuits. While on the other hand, FHE works with algebraic structures called polynomial rings that are very large and with a non-prime modulus. And they make a lot of use of these non-algebraic operations. So, well, and on top of that, there is also a problem with the fact that you are working with ciphertext. So there is something called ciphertext expansion, right? So a ciphertext is obviously larger than a plaintext. So proving a multiplication on plaintext will be different from proving it on ciphertext. On one hand, a normal multiplication is trivial, while the same operation in FHE would involve tensor product, mod switch, scaling, storing the whole trace of this operation would take kilobytes just for a single operation, and it would be orders of magnitude slower than the plaintext counterparts. So, well, this is just a hint on why this is hard. And indeed, I mean, you can try to take a snark and indeed prove the computation ciphertext. A snark is Turing complete, so potentially, theoretically, could prove anything, right? Well, the problem is, again, the fact that if you take just a normal snark, then you have problems for the prover, because then you would have to emulate the arithmetic over rings with the arithmetic over fields. You would have to prove non-algebraic operations. So overall, this would result in a proving time and a trace memory that are simply prohibitive. Well, here actually I listed 3 approaches. The first one is the one I just mentioned to you. Then there is another approach which takes a different step, which is HEIOP, which is actually running a snark under the FHE. With some advantages that now you don't have to prove anything on ciphertext, so it's super efficient, but it has some, as you can see, some problems that are inherent to the approach. Since, I don't know, the verification requires decrypting, it cannot be publicly verifiable, at least in the usual sense, and it's also weak to verification oracle attacks, so it's quite dangerous to use it. And one important thing is that it doesn't support all FHE schemes. For example, it doesn't. He's missing one important FHE scheme, which is CKKS. CKKS is, I would say, the FHE scheme that is mostly used for machine learning applications. So this is something we really care about. And then there is a third approach that is in our paper, appeared, I mean, it's one of my papers in last year, Crypto 25, where we actually designed snarks to work for FHE. And so that we now have, we don't have to do any emulation, we can work natively over rings. And we were able to prove most of FHE operations. And most importantly, we were also able to get CKKS. So I'll start from that paper. And the most important part of that paper is a blueprint. A blueprint for designing practical VFHE schemes. And it's a sort of recipe. And it starts with an FHE scheme that for us will be CKKS. It makes it proof-friendly, something I'm going to explain later. Then there is an arithmetization, which is a way to translate proof-friendly CKKS operations into something the SNARK understands. That in our case is relations over rings. And crucially, in CCC 25, we found that we only need two relations to express any FHE operation, namely arithmetic checks and range checks. And with that, we can run our SNARK, because that's the language the SNARK speaks. And the SNARK is defined as a combination of polynomial IOP, which is an information iterative path, combined with a polynomial commitment. The IOP, in turn, is made of a GKR-style protocol for the arithmetic checks and range proofs for proving range checks. And both things, everything has to be adapted to rings. So this is where you can find more about it. So thing is, we tested our blueprint for single FHE operations. And we found out that through experiments that the schemes we got were outperforming by orders of magnitude previous approaches, basically based on generic SNARK. So what do we do in this work? We start applying this blueprint to actual circuits. So we move from single FHE operations to something more concrete. And by so doing, we naturally face practical challenges, mainly related to memory, proof size, proving time. And in this paper, we try to fix them. So I'm going to talk about some techniques that allow us to improve on that. So oracle packing, batching, unimproved arithmetization, and something called sparse pack. Let's start with oracle packing. So the blueprint I showed you is entirely defined over RQ, because FHE is defined over RQ, right? However, not everything is about RQ. FHE works by scaling by integers, uses automorphisms, and most importantly for us, it uses infinity norm to bound the coefficients of RQ elements. So, for example, where would we use infinity norms? I'll briefly recap what the arithmetization looks like in CCC 25. Again, it's a way to translate FHE operations into relations over RQ. And I'm just giving you an example for a particular FHE operation that is key switching. You don't have to understand what it does. It's just that if you take this as a gate, and you try to prove it, then the red part is going to be a problem because it's something. It's basically a decomposition over several prime numbers. It takes an RQ element and it decomposes modulo several primes. This is not algebraic, so it's very hard to prove it without a significant overhead. So what we did was to allow the prover to send us a vector W that he claims to be the result of the gate that we don't want to prove. And instead, we check that it recomposes to the argument, to C1, through the CRT map, and that the components of the vector are bounded by the primes. And that tells us, if that verifies, that the vector W is the correct one, is the actual output of the CRT -1 operation. And with that, we can actually compute the output of the gate. As you can see, we separate to, we have two kinds of operations, the green ones that are algebraic, purely algebraic, and the orange one that is a range check and uses the infinity norm. So that's where we talk about ZQ elements. So that holds for pretty any homomorphic operation. So it produces these W's that we have to check. And the idea is that we collect all them together into a unique vector B, and we do the range check using a lookup. Pictorially, this is what it looks like. So we have a vector V. The rectangles are RQ elements. The squares are the coefficients. So if we want to prove that V, that the rectangles are bounded, we just do a lookup into this table that we construct just by taking all the RQ elements with coefficients bounded by TB, and we show that every triangle in V also appears in TB. Nice, except that it doesn't work because the ring is too big. So the table TB is just too big to be represented. So what we did was a decomposition following a lasso. We decomposed the bound B into a small base beta. So we reduced a big lookup of TB to smaller lookups into T beta. We end up into something like this, the smaller lookups. But again, they are too big because of the ring dimension. And so the solution in CCC25 was to decompose to through the ring dimension n. And eventually, we end up to this situation where we have integer lookups into a small table T beta. If we choose beta in the proper way, then this is a very small lookup that we can attack with memory checking techniques. And that's pretty much what we did in CCC 25. But now there is another problem. So this is what we got at the end. But we started with an RQ vector of size n. So from an RQ vector of size n, we ended up with something larger with a overhead around n, where n, again, is the ring dimension. So the question is, how do we commit to these vectors? Because at the end, we have only access to RQ polynomial commitments. So the solution we had back in CCC25 was to embed them back to RQ. So we take these integer vectors, and we place them into our queue, seeing them as the zero terms of the polynomials. Well, this works because now we have our queue oracles. But it's not a great solution because, as you can see, there is a lot of wasted space, the white space. And actually, it's an ODN overhead. And n is big, remember. But even worse, if you consider that the integer vector we got from the decomposition was n times larger than the original one, then we have an ODN square overhead, and that is too big. So the first solution in this paper was to get rid of this n using packing. So we keep an actual oracle to the original RQ vector, and we only create a virtual oracle to the ZQ vector. And then we link them together via a technique called packing and unpacking. In pictures, this is what happens. So we create an actual oracle to V and a virtual ZQ oracle to the big vector. So the range proof accesses and queries the virtual oracle. The rest of the protocol queries the RQ oracle, where it is defined. And the RQ oracle answers the range proof through the packing and unpacking technique. So basically, we don't have to commit to the big ZQ oracle. Result is that we don't get the n overheads. Then. Okay, and we can use it whenever we need commitment to ZQ. Second improvement is batch fold. So we need multivariate polynomial commitment for our ring. And in CCC25, we chose breakdown. Turns out that even though it's a linear time improver, the verifier is not really great. So now that we don't have the ODN overhead, we can use something that we can allow a quasi-linear prover to get a better verifier. And we chose basefold. That's just we could have chosen something else, but just to make it the verifiers faster, we chose basefold. Can we do better? Yes. So we have oracle access to polynomial evaluations, actually many polynomial evaluations. Most natural thing you can do is to batch them. So we take the original basefold and we modified it so that we can support batching. We call this scheme batchfold. So for m polynomials of size n, instead of having m log square n for proving and proof size, we now get that the log square term is separated from the batching parameter. This is nice because there is a big constant factor hidden over there. Can we go further? Yes. And we can use batching to speed up even a single evaluation of the polynomial commitment over RQ. But first, let's have a look inside RQ. So this is our RQ that splits through RNS and another round of CRT into a product of smaller extension fields. So for concrete efficiency, we would have chosen d equal to 1, but this is not great for our proof system because these are not that big. Then we chose d equal to 4 so that we can get both fast arithmetic using incomplete NTT and also get soundness. So this is how what our ring looks like. Now, the way that our polynomial commitment is designed is that it splits according to the ring splitting. And so for each prime, these evaluations over the isomorphic components of the ring can be seen as multiple polynomial evaluations. So we can batch them using the isomorphism. And that's great, because then we can speed up a single polynomial evaluation. So if n is the ring dimension, L the number of RNS components, then we get that instead of having n, L, m log square n, we again separate the square factor from the dimension of the ring n and the batching factor m. And again, the heavy part lies over there. So this is the comparison with normal basefold, and we get that a single evaluation is even 3 times faster, and the proofs almost 10 times shorter. Third improvement is a better arithmetization. So, for example, how do we prove a circuit? So we start with a circuit for, I don't know, a neural network. Then we get the encrypted version of it in I don't know, using CKKS. And then there is the arithmetization that produces the GKR circuit over RQ. Now, the GKR circuit will have wires, gates. This is just an example of gates. And we have to encode this circuit. And we do that using multivariate polynomials. So we do that for wires. We do that for gates. Now, the thing is, this is quite easy for gates. They have the same dimension as the circuit. But for wires was easy. For gates, you see that the polynomials now are cubic in the size of the original circuit, and we cannot commit to this. So what we do is we prepare a description of the circuit that depends on the FHE part that is succinct, let's say, so the verifier can evaluate it. And for the rest, the thing that doesn't depend on the FHE circuit, it's arbitrary, we do a better arithmetization that allows us to express it with less sparse polynomials. And we also have a protocol for evaluating these big sparse polynomials that is more efficient than existing techniques I'm going to talk about in a moment. This is actually what we do, and this is actually the last part. And it's the circuit preprocessing. So the part of the circuit that doesn't depend on FHE, it's something that the verifier has to commit to and possibly delegate the evaluation to the prover. The polynomials are very sparse, are big, cubic in the circuit size, but they have evaluations in ZQ. So that's where we can use our packing technique, and we use also batching, and we get a new protocol for evaluating sparse polynomials. And we outperform other techniques that were not suitable for our ring. So for the results, we consider as an example, we consider a small neural network circuit, so just 3 layers, 3 inputs to outputs, and we approximate the activation function with the square function, and we consider different configurations of the neural network. So as you can see, the sparse representation of the circuits is big, around cubic in the dense polynomial size. And when we go to, and then we tested our sparse back for evaluating the polynomials that encode the circuit. And we got an improvement over Spark that is it was a previous technique for doing the same. Important thing is that we don't have to execute commitments on the fly, and we get, in general, better evaluation times. So the last thing is range proofs. So for the range proofs, they are actually the most expensive part of our protocol. The rest is basically negligible. And we got these numbers using a single thread execution. We would get, using more threads, we would get even better efficiency. We cannot directly compare with CCC25, but the improvement would be around 100 times. So conclusions is practical VFHE is hard because FHE snarks work on different worlds. Ciphertexts are big. In CCC25, we got a first blueprint for realizing practical VFHE that improved generic approaches for single FHE operations, while in this work, we try to scale up to concrete circuits. So even though the circuits that now we are covering are kind of small, as you can see, it's a two-layer neural network, still, this is a theoretical improvement in the sense that we are basically where FHE was around 1 decade ago, and there is more and more to come. Thanks. Questions?
Thank you, Daniele, for your talk. I think we're running slightly behind the schedule, so let's proceed to the next speaker.
Nice talk.
The next talk, while loading the
Testing.
slides, is going by be given by